So let us now come to how these two are related, and this is an important theorem. So let us say G is a group. Always this is our setup in these videos. G is a group, S is a set, G acts on S. Okay, so then in this situation there exists a bijective function. There exists a bijective function phi from G mod the stabilizer to, okay, so fix, let a small element S be taken in capital S. Okay, so let me repeat the theorem. G is a group, arbitrary group acting on an arbitrary set S, and let us fix an element of the set small s. So small s is an element of capital S. Then there exists a bijective function between orbit of S, this is the orbit of S, and G mod GS. What is G mod GS? G is a group, GS is a subgroup. So G mod GS is simply the set of left cosets of GS in G. I must remark here that this is not a G mod GS, not a group, because GS is not necessarily a normal subgroup. Okay, so this is just a warning to you that when I write G mod GS, typically it is used only when you have a normal subgroup and you consider the quotient group, but here I am using the notation for convenience to denote the left cosets of this subgroup in this group. GS is a subgroup of G, not necessarily a normal subgroup. So this is, in this theorem, you only think of G mod GS as the set of left cosets. So the proof is not difficult at all, okay, with all the setup that we have so far. So G mod GS, there is a bijective map from G mod GS to OS. So, and actually define, so this should also be part of the theorem. Define phi of, what is a left coset? It is of the form G times GS, right? G mod GS is the set of left cosets. So it is small g times capital GS. Define this to be GS, right? This is of course in the orbit. So what is the function? It is taking a left coset, which by definition is of the form G times GS, and I will map it to the element GS, which is in orbit. So we have to check first of all that this is a well defined map, because a left coset can have several representations with a different G here. Okay, so phi first we must check is well defined. Phi is well defined. Okay, why is that? So suppose GGS is equal to G, let's use HGS. We must ensure phi of G equals phi of H. That is, we need to check GS equals HS, right? This obviously needs to be checked because we are trying to define that image of G times GS is GS, but it can very well happen that GGS is equal to HGS, but G and H are different because several cosets will coincide, right? But then if GGS is equal to HGS but GS is different from HS, then there is a problem. The function is not well defined. So we need to check this. But this is not difficult at all. If you if you start working this out, it will become clear. So if GGS is equal to HGS, then what do we have? This implies that G equals some H, let's use a G prime for some G prime in GS. Right, this is clear to you, right? If you have two left cosets are equal, okay, so then I'm going to just quickly work this out. So in general, if you have two left cosets, so G is a group, H is a subgroup. If you have GH equals G1H equals G2H, then remember G1 belongs to G1H, because G1H is the set of G1 times every element of capital H. In particular, G1 times identity will be one of the elements of G1H. So G1 is in that, which I am assuming is equal to G2H. So G1 belongs to G2H. So G1 equals G2 times for some H in capital H. I am using the same idea here. G times GS is equal to H times GS. So G must be H times something in GS, right? Now this implies if I do GS, now let's apply both, bring in the set here, the element S here. GS equals HG prime S, right? Because G is equal to HG prime. But the group action property says that HG prime S is equal to HG prime S. But G prime, remember, where is G prime? G prime is in the stabilizer. Since G prime is in the stabilizer, what does the stabilizer mean? This is all elements in capital G that fix S. So G prime is an element of the stabilizer, means G prime fixes S. So G prime S is equal to S. So H of G prime S is just HS. So we have concluded that GS equal to HS as required. So if two left cosets GS and HGS are equal, GGS and HGS are equal, we concluded that GS equals HS. So there will be no problem. You can choose one representative, I can choose another representative, and we apply both the function phi, we both get the same answer. So GS is equal to HS. So that's good. So phi is well defined. Now we are trying to say that phi is a bijection, right? So phi is well defined is all well and good, but we want to check that it is 1 1 and on 2. Why is 1 1? Phi is 1 1. Let's check that. What does this mean? 1 1 means if phi of GS equals phi of HGS. Suppose this happens. We want to conclude that GGS is equal to HGS. Let's work it out. Phi of GGS equals phi of HGS. I am taking two elements of the left hand side domain, which is G mod GS. So I am taking two elements GGS and HGS. Suppose phi of them are equal, phi of these two elements are equal. Then that means GS is equal to HS, because phi of GGS is just GS. GS equals HS. But this means if you now say H inverse GS is S, okay, this is something that we have done before. You multiply by H inverse on both sides on the left hand side. So H inverse GS is equal to HS. H inverse HS, which is S. H inverse G applied to S is S. This is 2-3 steps are missing here. I am not writing all the steps because we have done these things, the same calculation before. But this means H inverse G fixes S. So it is in the stabilizer of S. So H inverse G is in the stabilizer of S. But H inverse G is in GS. So H inverse G times GS equals GS. Remember that if you have an element in the group, the left coset determined by that element is the identity left coset. So H inverse G GS is equal to GS. but this means GGS equals HGS, right? So we have a function from G mod GS to orbit of S. If two things map to the same thing, we are saying that they are equal, right? So this is 1 1. If GGS and HGS map to the same element, namely phi GGS is equal to phi HGS, we concluded that GGS is equal to HGS. So phi is 1 1. This completes that proof. Finally, is phi onto what is an element in orbit of S? What is an element of it is of the form a typical element for some G in G, right? An element is simply of the form GS. Then we have phi of, you take the same G, GS is equal to GS, right? So ontoness is very clear here, because the elements of orbit of S are by definition of the form GS. Now for the same G, GGS maps to GS. So phi is onto, and this completes the proof that phi is a bijective map, right? So this is how we relate the stabilizer and the orbit. There is a set theoretic bijection. Let me emphasize that, because the OS is just a set, G mod GS is in general just a set. So there is just a bijective map from G mod GS to OS, namely given by a coset GGS maps to G times S, right? This is the important definition of the function, and once you have the function defined like that, it is relatively easy to check that it is well defined. It is 1 1 and around 2. So now let us see what are the applications of this theorem. So the theorem says that, I called it a theorem, I guess. Yeah, so I called it the theorem. The theorem implies the cardinality. Okay, so now I am going to use the symbol, is denotes the number of elements Okay, we have used that to denote the order of a group. So let's just extend it to denote order of any sets, a group or cardinality of any set. So the number of elements of a set is denoted by vertical bars, right? So if two sets are in bijection, then the number of elements in those two sets are equal. This will be most useful when the group and the set are finite. Okay, so let us assume that G is finite. So we need only G is finite, orbit will be finite, S may not be finite, doesn't matter. So I am going to assume G is finite. Recall the counting formula. What was the counting formula that we proved when we talked about cosets of a subgroup in a group? If G is a group, H is a subgroup, we said that the number of left cosets is equal to the order of the group divided by order of the subgroup. So G mod GS, which was denoted in our earlier videos by this, the index of, this is the index of GS in G, index of GS in G, this is equal to order of G divided by order of H, right? So let us written differently, we have order of H, H is GS here, so GS times the index of G in GS is order of G, right? So I'm just rewriting the counting formula. In our case, in our situation, the index of GS in G is, by the theorem that we just proved, remember this is all relative to, all of this is relative to the fixed element, small s in capital S. So every time you see small s here, I am referring to that fixed small s. So in our situation, the index of GS in G is the orbit size. So we have the order of the stabilizer times the size of the orbit is equal to the order of the group. Okay, this is a very important application of the theorem that we proved and the counting formula. This is also called a counting formula. Okay, this is in fact very similar to the counting formula that we had earlier, namely G, the index of a subgroup in a group G is the ratio of the orders of the two subgroup group divided by the subgroup. Applied to this particular case of the group action on a set, we have cardinality of the stabilizer times cardinality of the order is equal to the cardinality of the group. And this is a very important, and has many applications. We will see these in later videos. Let me only say at this point that, for example, we can immediately conclude that the size of an orbit, let me say the number of elements in an orbit must divide the order of the group. This is not really clear, right, in general. Why would, so if a group G acts on a set S, you took an orbit which is a subset of the set S, why should that size of that orbit be related to order of the group? It's not clear, right? Group is here acting on a set S, orbit is inside the set. Why should the size of the orbit be related to the order of the group? And this is a consequence of the counting formula. It is not only related, it is related in a very precise way. Size of the orbit must divide the cardinality of the group, the size of the group. So this is very useful observation which tells us that orbits, the sizes of orbits are not arbitrary, right? They have to satisfy the property that they divide the order of the group. So this reduces the choices and helps us compute the odd bits in many situations. This is the counting formula. So I want to do one more application of orbits partition the set S, right? So let us apply this, orbits partition the set S. So assume now that S is finite. Everything that we have said until this point, the set S need not be finite, okay, because even in the counting formula the size of S is irrelevant, only the size of orbit is relevant. So in particular I should say that the counting formula says that if G is a finite group acting on an infinite set S, the orbits are still finite, okay. So that is a consequence. Orbits cannot be infinite because orbit size must divide the group size. The set S may be infinite but the orbits must be finite. But now I am going to assume that set is also finite. Then we have S must be a disjoint union of orbits, right? Because orbits are equivalence classes under the equivalence relation that I defined at the beginning of this video. So they are of the form OS1 union OS2, and the symbol for disjoint union is this, denotes okay. This symbol simply means you are taking the unions, but it in addition it says that the sets involved are disjoint. Right? For some because S is a finite set, obviously there are only finitely many orbits, and if you take the distinct ones among them, they are all disjoint and they cover S. So in particular we have the order of the set S is equal to order of the orbit S1, orbit S2, orbit Sk. Okay, this is another important counting formula. This is also related to the counting formula. It says that if S is a finite set, then S can be written as a sum of orbits. The cardinality of S, number of elements of S, can be written as sum of some orbits, and because of the counting formula that I did in the previous slide, each of these numbers here is a divisor of the cardinality of the group, right? So we have a very strong restriction here. So the size of the set S is a sum of some numbers, but each of those numbers divides the order of the group. So we are going to exploit in later videos this very important observation that we made. So let me recall, we have made two observations in this video. One is that if G is a finite group acting on a set S, the cardinality, and you fix an element small s of capital S, that's very important. You fix, this is for a fixed element small s in capital S. The stabilizer order times the orbit order is equal to the product of the stabilizer and orbit is equal to the cardinality of the group itself. This in particular says as one consequence that the number of elements in an orbit must divide the order of the group. And another way of using the partition of S into orbits is that if S is a finite set, the number of elements of S is equal to the sum of number of elements in some orbits, and each orbit size divides the orbit of the group. Let me stop the video here. In subsequent videos, we are going to exploit these counting formulas that we proved in this video. Thank you.